types of functions we're going to deal with in this chapter are going to be polynomial function. That's x's raised to integer powers. Let's look something like this. X cubed plus 7x squared minus 3. That's a polynomial function. X is raised to integer power, positive integer powers. Trigonometric, it'll have a sine, a cosine, tangent, secant, cotangent, or cosecant in it. The domain of polynomials, by the way, all real numbers. You can cube anything, square anything, multiply anything, add, subtract anything. There's no restrictions on polynomials. Trig functions, sine and cosine are your friends because all real numbers. Everything else is a little bit more ugly. Basically, this is the algebraic structure of the domain. Pick a number. Chris, pick an integer. 3. So negative 3 pi over 2. 3 plus 2 is 5. 2. That's not right. Yeah, it is 5 pi over 2. All right. That could be a domain of tangent and secant. All right. Suppose we're looking for from 1 to 2. All right. 5 pi over 2 is about 7 point something, and negative 3 pi over 2, that seems like it's really large. I have that written wrong. Negative pi over 2 to pi over 2. I think this should just be I don't think this n plus 2 is supposed to be there. Something's wrong with this one, I'll fix it. I don't want to do a long report. There's something wrong with that one. Alright, well, let's suppose we have this one. So if we pick like 3 on this one, 3 pi to 4 pi. Cotangent and cosecant. Alright, that is, so 3 pi is 9.42, 4 pi is 12.56. So if we were going from 9 to 10, that would be a sufficient interval. From 0 to pi, from pi to 2 pi, from 2 pi to 3 pi, and so on. So you could just say that all those domains, as long as you're not doing, as long as you're not crossing over pi, you know, you're in good shape there. Every problem we do is going to work. So just know that the domain you get will be the right domain. Rational functions, you can't divide by 0. So if the denominator doesn't equal 0, that's part of the domain. So let's say we're doing 1 over x minus 3. That's a rational function. What can x not equal? 3. So if we want to make sure there's a root between 1 and 2, and x is not allowed to equal 3, every number between 1 and 2 is legal, right? Yeah. So that's basically what we're doing here. And then a root function, that's the square root. Let's say, of x minus 4. You can't have, the radicand cannot be negative, so we do x minus 4 is greater than or equal to 0. So that means x is greater than or equal to 4. So if we want to prove there's a root between, let's say, 5 and 6, 5 and 6 are both greater than 4, so that would be legal. All right, so that's kind of the idea here, that every one of these has a domain. All right, and when we look at our procedure, our first job is to determine the domain of the function. All right, and state that the interval we're working with is a subset of that domain. So if I was doing a problem involving this, and they wanted me to prove there's a root between 5 and 6, I would first establish the domain of the function. That's the domain, and then I would state this is completely inside that domain. All right, that's kind of what step 1 is. Step 2 is to establish the type of function it is. It's going to be one of these 4 or a mixture. If I have x squared plus sine of x, that's both a polynomial and a trig function. So you'd say it's both polynomial and trig. It still establishes domain. That's all real numbers, so whatever they give me is going to be in that domain. All right. After we establish what type of function is, evaluate it at the endpoints, and again, we should get opposite signs. And the way it works is this. It's real simple. What did we learn about continuous functions yesterday? Something's continuous, what does it not have? It doesn't have any breaks. Okay? So if we have some interval from a to b, we have a continuous function that has no breaks in it. F of a is a positive answer, f of b is a negative answer. Is there any way for me to get from here to here without crossing the x-axis? No. And if it crosses the x-axis, it has a root, right? Yeah. All right. So that's all the intermediate value theorem is saying, is you have a continuous function on a domain from a to b, has no breaks. F of a equals some number, f of b equals an opposite sign number. To connect the dots, you have to cross the x-axis, therefore there's a root. That's all it is. That's all the intermediate value theorem. It might cross once, it might cross a bunch of times. It doesn't matter. the goal is to find out there's at least one root on the interval. That's what we're doing here. All right. So everything we're doing in this procedure, determine the domain. So if the domain is from here to here, there's no breaks. All right. It's continuous. All right. The interval's a subset. So if the domain's here and your interval's here, it's on that continuous curve. We're in good shape. Stating the function, what type of function is. Every one of these are officially continuous on their domain. So we're going to determine it's one of these types of functions that's always continuous on its domain. Evaluation ensures we have one positive, one negative result. And if all three of those things meet, we have a continuous function, we have the positive, negative, the graph has to cross the axis. So we can say by the Intermediate Value Theorem, which states specifically, if all three of these things happen, then you have a root. All right, that's what the Intermediate Value Theorem says. So let's try it. Use the Intermediate Value Theorem to show that the equation y equals 3x cubed minus 2x plus 2 has a root on the interval -2, -1. So step 1. The domain is all real numbers and -2, -1 is a subset of all real numbers. That's what step 1 should look like every single time. Tell me what the domain is and establish that the interval they're concerned with, which specifically this interval is what they're concerned with, lies within that domain. That's all step 1 is or ever will be in this process. All right. Why is it all real numbers?
Because it's a polynomial.
It's a polynomial function. The polynomial function, domain's all real numbers. Okay? So, if you're dealing with a polynomial function, it's pretty straightforward. Every interval is a subset of all real numbers. It's all real numbers is negative infinity to infinity. Any numbers you pick are between those. So, right, that's pretty straightforward. Step 2. I want to establish my function. I'm going to call it f of x equals that function, 3x cubed minus 2x plus 2 is a polynomial function. That's what step 2 should look like every time. The function, I call it f of x, that way I can refer to f of x each time instead of having to rewrite this function every time. Name it something. Function equals the expression is a polynomial function. Tell me what kind of function it is. Step 3. The numbers I care about are -2 and -1, so I want to do f of -2 equals and f of -1 equals. All right, f of -2 and f of -1 just mean to change x to -2 and -1 and evaluate. So if I put -2 in place of x, I get 3 times -2 cubed, which is -8, minus 2 times -2 plus 2. That comes up to -24 minus 4 plus 2, which is -26. F of -1.
Would it be plus 4?
Oh, it would be plus 4. Thanks, Chris. Plus 4. So -18. Good catch. All right. So f of -2 is -18. It's a negative result. F of -1, 3 times -1 cubed minus 2 times -1 plus 2. That gets me -3 plus 2 plus 2, which is 1. Okay? The requirement of these two results, one has to be negative, one has to be positive, which they are. So if I was to graph this on graph paper, you don't have to graph it, but just to real quick take a look at that. If I was graphing this on graph paper, put 2 pages so I have more room. -2 gets me -18. So -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right here. And -1 is 1. We have a polynomial function, and it's continuous from -2 to -1. We've already established that. This is negative, that's positive. It has to cross the x-axis somewhere in there. I don't know where it crosses, but it has to cross between those two numbers, right? There's no way to get from this point to that point without crossing the x-axis. That's all the intermediate value theorem is about. You have a no-break function on the interval you're dealing with. One's negative, one's positive. There has to be an answer. All right? So, the last thing we do, and every single problem ends like this, by the intermediate value theorem, f of x has at least one root on -2, -1. Step 4 looks like that every time. The only thing that changes is the interval. Every other word in that last statement is exactly the same every time. By IVT, comma, f of x. If you choose to call it f of x, you call it g of x, that's on you. I call it f of x every time. Right? But whatever you've named the function has at least one root on whatever the interval you're dealing with is. The only thing that should change in this sentence is that interval, because different problems have different intervals. That's the entire proof, and that is an actual proof, that that has at least one root.
Circle the whole thing.
That's the answer, yes, the whole thing's the answer.